All right, we're going to get started on section 8.3, and in this section, we're going to look at the composite numbers that have actually primitive roots. Recall in section 8.2, we proved that every prime has a primitive root, and in this section, the main objective is to determine the composite numbers that have primitive roots. In fact, the list is going to be very short. There are infinitely many, but as far as the different types of numbers, it is not, very many types of numbers they're going to have primitive roots. And this is what we're going to be actually showing. The idea is we're going to prove some theorems which rules out certain numbers to be, to have primitive roots. And then we're going to say that certain types of numbers, they're going to have primitive roots and show that these types of numbers, in fact, do have primitive roots. So two types of argument. One, there are some numbers, they are not going to have primitive roots. And in another argument to show that the remaining kinds of numbers, they will have actually primitive roots. All right, so we're going to start with the first type, that there are some numbers. They don't have primitive roots. In particular, all powers of 2, where the power, the exponent is bigger than or equal actually to 3. All right? So here it is. So this is the first term. 8.7, and treats like this: 2 to the k has no primitive root. For every k bigger than or equal to 3. All right? So here's the proof. Of course, we need to take a number that is relatively prime to 2 to that k. That's the number that we're going to show that has no root. So this number must be an odd number. So let A be an odd positive integer. And we're going to show that for every, so here's what we need to show. For every k bigger than or equal to 3, we have this congruence relation actually holds. A to the power 2 to the power k minus 2 is congruent to 1 mod 2 to the k. All right? And we're going to show that this actually does hold. All right? So we're going to do this is by induction. All right? By induction on k. So for k equal to 3, that's the smallest value, we have A to the power 2 to the power 3 minus 2, and this is going to equal actually A squared. All right, and this is congruent to 1 mod A. So this is what the congruence relation becomes like, and this holds for all the integers for A equal to 1, 3, it becomes 3 squared, that's 9, congruent to 1 mod 8, yes, and 5, so it gives you 25, congruent to 1 mod 8, yes, because the difference is 24, and 7, give you 4 to 9, and of course for numbers, so if, of course, A is bigger than or equal to 8, we reduce mod A. And we're going to get, actually, for those to be relatively prime, it's going to be one of these A's. So it actually, this means the congruence actually holds. So in other words, the base system actually holds. So now let's set the induction hypothesis. The inductive step. We need to assume that this congruence relation holds for some k. So and assume that a to the power 2 k minus 2 congruent to 1 mod 2 to the k for some k bigger than or equal to 3. So we're going to consider the congruence relation for k plus 1. We're going to consider the congruence relation for k plus 1. And to do this, so we're going to, so what does this mean? What does actually this mean? So this implies that 2 to the k divides a to 2k minus 2 minus 1. And this implies that a to the 2k minus 1, or sorry, minus 2 is equal to 1 plus b to the power 2 to the k. All right, for some b in z. Okay, by definition of congruence. All right, now we're going to square both sides of this equation. So we're going to square both sides of the previous equation. And this is what we get. We get a to the power 2k minus 2 squared. And this is equal 1 plus b times 2 to the k squared. All right, well, let's simplify this and see what does it look like. So in other words, this k for k plus 1 is going to come out of this, basically. That's what we're going to see from these calculations. So we're going to go in here. And we have this one becomes a to the power 2k minus 2 multiplied by 2. We just multiply the exponents. And the other side becomes 1 plus twice b times 2 to the k plus, this is squared, b squared to 2k. Well, so this side becomes a to the power 2 to the power k minus 1. We're just going to add the exponents. So we reduce that exponent by 1, increased by 1. And this is equal 1 plus b times 2 to the k plus 1. And plus b squared. And this one is 2 to k, 2k. All right. Now, let's apply, to do it congruent. So, so we have this is going to be congruent to 0 mod 2 to the power k plus 1. And actually, let me factor out from here. Let me do one more thing. Okay, let me do one more thing. To take care of both of these. So this is equal to 1 plus, we take a k plus 1, a common factor, so this becomes b plus b squared, and this becomes 2k minus 1, all right? So when I multiply them out, we come up with 2k actually minus 1, and that's what we have. Now, this one is congruent to 1 mod 2k plus 1. Because there is this factor in here, so this whole thing becomes congruent to 0 mod 2k plus 1. Okay, so in other words, yes, and the left side is actually the what it's supposed to be the left side for the case k plus 1. So this one is a to the power 2k plus 1 minus 2. All right, and this is congruent to 1 mod 2k plus 1. So this holds. This is what I have shown. So therefore, the statement or the congruence relation holds for k plus 1, and by math induction, the statement, the congruence, which is a to the power 2 k minus 2, is congruent to 1 mod 2 to the k for all k bigger than or equal to 6. All right. Now we're going to look at actually the to see what's the order of A with respect to or relative to or mod 2 to the k. All right. So we need to see if this as a primitive root means it has an order of phi to the k. So we're going to look at phi 2 to the k. So by the formula for calculating this is equal to the k times 1 minus, there's only one prime factor in here, which is 2. And this becomes 2k minus 1. All right? Now, then, and this is actually is equal to, all right, or let me look at actually 1/2, instead of 1/2 phi to the k. So this is going to be 2 to the k minus 2. And then we have shown, so this congruence relation, let me write it down in here. We have shown 2 to the power 2 to the k minus 2 is congruent to 1 mod 2 to the k. Remember, this is for every k bigger than or equal to 3. So this is equivalent to the same as replacing the exponent. Sorry, this is not 2. This is a. This is a. So this is equivalent to saying that we're going to write it in terms of the phi. So this one is equivalent to saying that a to the power of 1/2 phi of 2 to the k is congruent to congruent to 1 mod 2 to the k. And this implies that the order of A with respect to or mod 2 to the k is going to be less than or equal to 1/2 phi of 2 to the k, because this exponent actually make this is congruent to 1. So the order must be smaller than this, which means this is not, and this is of course not equal to phi of 2 to the k, since k is bigger than or equal to 3. Yeah, to 3. In fact, it's bigger than even or equal to 1. This is not equal to 0. This means that the order of A, again, mod 2 to the k is not equal to this, which makes this A is not a primitive root. So this makes A, or 2 to the k has no primitive root. Has no primitive roots. Because A was an arbitrary integer, and the order of it is actually not equal to phi of 2 to the k, not make it into a primitive root. All right. Now let's look at the second type of composite numbers. They don't have also the primitive roots. So this is the first type, which is powers of 2. Okay. Theorem 8a. Give us the other type. If m, n are integers, each one of them is bigger than 2, and are relatively prime, then their product has no primitive root. Then n has no primitive roots. All right. First, let's start with taking an integer that's relatively prime to the product. So let's take A in Z such that greatest common divisor A and n equal 1. This greatest common divisor equal 1 implies there exist x and y in Z such that A x plus m n y is equal to 1. And we can rewrite this as A x plus m n y equal to 1. And we could think of n y as y prime. So this is a combination of A and m. All right, equal to 1 means A greatest common divisor of A m equal to 1. Similarly, we have rearranged this in a different way. Similarly, a greatest common divisor of A and n is equal to. All right, now we need to look at since m n are bigger than 2, this implies that the phi of m and phi of n, both of these are are even. All right, I've shown this earlier. And this means that the greatest common divisor, so the greatest common divisor of P of M, P of N, actually it's going to be bigger than or equal to 2. And I want to denote this by D. All right, so this implies that D is bigger than or equal to 2, or we're going to use actually the reciprocal. 1 over D is less than or equal to 1. Also, I need to denote the least common multiple of phi of M and phi of N by the letter H. So we're going to let H equal least common multiple phi of M, phi of N. All right. Now let's look at what this is equal to. Of course, this is equal to, we have a formula which tells us that this is the product. Everything is positive here, we don't need absolute value, divided by the greatest common divisor of phi of M, phi of N. And this is equal the product. And yes, and then I'm going to say this is less than or equal to, all right, and actually 1/2 phi of M, phi of N. Because we have the greatest common divisor, this is D, is smaller than 1/2, all right? So we have this inequality between. Now let's look at applied Euler's theorem. By Euler's theorem, I can take a to the power, because A and M are relatively prime, so A to the phi of M is congruent to 1 mod M. Then I want to raise both sides of this of this congruence, previous congruence, to the 1/2 phi of N exponent. In other words, I want to get this H to be in the picture. All right, so let's see what does this give us. So we have A to the phi of M, raise this to the 1/2 phi of N. And this is, of course, congruent still to 1 mod N. All right, so we have this congruence relation that holds, that is 1/2 phi of M, phi of N is congruent to 1 mod N. Similarly, we can reverse and apply Euler's theorem to N, phi of N, and then raise both sides to the 1/2 phi of N. So we get another relation, all right? Similarly, we have A to the 1/2 phi of M, again phi of N, is congruent to 1 mod N. Now, since M and N are relatively prime, I can multiply these two congruences and come up with a congruence mod their product. Okay? So since greatest common divisor of m in n is equal to 1, this implies a to the power 1/2 phi of m, phi of n is congruent to 1 mod m n. All right. Now, this means that we have and this implies that a to the power h, remember h is actually, if we, go back in here, I want to actually not do 1/2, I want to do this one over d. Sorry. Let me put this is over d. Okay? Because I need to get the h. Okay, so this is divided by d, the greatest common divisor, to get h. All right, and so we have this one is still d here, and divide this is by d. Now, this is equivalent to saying that a to the h is congruent to 1 mod m n. And this in itself, it says that the order of relative to mn of a is going to be less than or equal to h. All right, and h, remember, the least common multiple. But h itself is less than or equal 1/2 phi of m, phi of n. And definitely 1/2 of these, because neither one of these is 0, and this is of course not equal to their product. So this means that any a that is relatively prime to mn, its order is going to be not equal to, so this implies that the order of a mod mn is not going to equal to phi of m, phi of n, for any a relatively prime to mn. And this means that mn has no primitive because always the order does not reach the maximum order of of course, this is equals, since these are relatively prime, also equal to this. All right. All right. Now, with this, we can state a corollary which rules out different types of numbers that they are not. They don't have basically primitive roots. They actually have the whole list, which does not have primitive roots. So here's the corollary. All right. First, if an integer, of course here it's a positive integer, n, all right, actually bigger than 1, all right, has two distinct odd prime factors, then n primitive and this follows from theorem 8.8, right? Because it says that so the 2 prime factors, they're going to be bigger than 2, all right? Because they are, and so if it has those, so n is going to have it's a product of 2, at least 2, odd primes. Each one of them is bigger than 2. Second, right, is if n equal 2 to the m times p to the k, where p is an odd prime and m bigger than or equal to 2, k bigger than or equal to 1, then n has no primitive roots. Yeah, let's see why this is true. So n is a product again of 2 relatively prime numbers, and the m bigger than or equal to 2 makes 2 to the m bigger than 2, all right? So it's going to be 4 at least. And so this means this one is okay, and this one is an odd prime. So if k is bigger than or equal to 1, this is going to be bigger than or equal to 3. So this is again a product of 2 numbers that are relatively prime and bigger. Each one of them is bigger than 2. So it's by the theorem again has no primitive roots. The third one, kind of a generalization of B, says that if n equal 2 to the m multiplied by any odd, okay, where m bigger than or equal to 2 and a is an odd, integer greater than 2, then n has no primitive. Again, the same reasoning. So means n is a product of 2 relatively prime integers. Each one of them is bigger than 2, so it doesn't have primitive roots. All right, so this is a big list of numbers. They don't have primitive roots. Now, next, we need to look at the numbers which they have the primitive roots. And so we are now in a position actually to state the main theorem, which give the list of all numbers that they have primitive roots, or what we call characterize those numbers they have primitive roots. And this is the last theorem in this section. I just want to put it in here, and then prove it through actually successive lemmas that will lead to the proof of this theorem. So this is theorem 8.10. This theorem was stated and proved by Gauss. Very important theorem in number theory, which gives the those numbers that they do have primitive roots. And this is the list. So an integer n bigger than 1 has a primitive root at least 1, all right, and then we know that it has phi of n different distinct primitive roots, all right. If I know there, n equal to 2, 4 p to the k to p to the k, where p is an order prime, and k is an integer that is bigger than or equal to 1. But as I said, the list is limited, okay? There's not many variety of numbers. However, because there are infinitely many primes, there are infinitely many, numbers, they have primitive roots. It's here, and of course, multiples of 2. But this is it, okay? So these are the only numbers which they have a primitive root. All right, so our objective in the remaining part of this lecture, it's going to be a while, is actually to arrive at this list of numbers. Each one of them has a primitive root. All right, first we have already shown that if P is a prime, then P has primitive roots. So our next objective, we're going to look at, we consider primitive roots for powers of primes. So a natural question is to ask if a certain prime, if R is a primitive root of an other prime, let me say this is is an R prime. Right, this is actually what we showed. This is in section 8.2. Okay, section 8.2. The prime 2 by itself is very easy. We can actually just do it by finding what the primitive roots of 2, and of course 4, which is the square of 2. And these are the only odds and powers of even and power of even prime. So 8, it doesn't have primitive root. Actually, this is covered by the first 8.7 theorem. All right. So next, we're going to consider primitive roots for powers of other primes. All right. So if R is a primitive root of an odd prime, then it's natural to look, then it is natural to consider whether R is a primitive root for powers of P. Okay, so this is the first thing. In other words, are there any, the primitive roots that primitive roots for P could be also primitive roots for example, P squared, all right? And so this is what we would like to look at. And then we're going to look at P to the power 3 and any power of prime. All right? So here is the question is the following. So here's a question you want to ask. Let's start with let B be at R, sorry, R be a primitive root of P. Now remember, P is R the prime from here on, all right? So we want to find under what conditions R is a primitive root of P squared. Let's start with this. All right. Well, R primitive root of P implies that R to the phi of P, which is equal R P minus 1, is congruent to 1 mod P. And this is the smallest exponent actually to make this congruence relation holds. Now, since phi of P squared, this is equal P squared times 1 minus 1 over P. And if I simplify this, this becomes P times P minus 1. And this is definitely bigger than P minus 1. So in order for R to be a primitive root, of P squared, we have a necessary condition basically. It is necessary to have R to the power P minus 1 is not congruent to 1 mod P squared. Okay, let me explain this. Because if R to the power P minus 1 is congruent to 1 mod P squared, then the order of this mod P squared is going to be less than, all right, that phi of P squared. So this need not to be satisfied in order for it's necessary condition. It turns out that also this condition is sufficient. It turns out this condition is also sufficient. Means if this condition is not satisfied, then R is going to be actually a primitive root for P squared. Okay? And even more, it is actually sufficient condition for all powers of P. Okay, sufficient condition, also sufficient condition for, we continue up here. For R to be a primitive root for P squared and in general for P to the power K for every K bigger than or equal to 1. Of course, because it's a primitive root for P is for K equal 1 and any higher exponent of P. Well, this is remarkable, okay? Means a necessary condition turns out also to become sufficient. Means if and only if. All right, that is what we need to show next. All right. First, I want to show, yes, in fact, if R is a primitive root, always I can find an R, all right, that actually satisfies this condition, all right? So this is the first lemma, all right? So the first lemma, we're going to show that there exists a primitive root of P that satisfies the condition. So to actually we put it as a lemma. Lemma 1. So it goes like this: if P is an R prime, and then there exists a primitive root R of P such that R to the power P minus 1 is not congruent to 1 mod P squared. Means satisfy that necessary condition. All right? And here is the proof. Of course, we already have shown that by theorem 8.6, P has a primitive root. Let's say R. All right? If it happens that if R to the power P minus 1 is not congruent to 1, either this one is congruent to 1 or not congruent to 1, mod P squared, then we are done. So let's assume, no, it does. Assume that R to the power P minus 1 is congruent to 1 mod P squared. I want to consider another integer related to P. So we're going to define an R prime. So in this case, we're going to let R prime is equal R plus. I claim that R prime is a primitive root of P. Well, R prime is equal to R plus P, and this is of course congruent to R mod P. And we have shown that if two integers, they are congruent to each other, then they must have the same order. So this means that the order of R prime mod P is the same as the order of R. And this, since R, we have it as a primitive root, so the order of this is phi of P, so this means that R prime, yes, is a primitive root. Is a primitive root. Now, I claim that this R prime does satisfy the condition, means it's not congruent to 1 mod P squared. All right, so here's the claim. R prime to the power of p minus 1 is not congruent to 1 mod p squared. All right? To do this, let's actually do expand the. So let's consider what r prime to the power p minus 1 is going to equal to r plus p to the power p minus 1. And by the binomial theorem, this is equal r to the power p minus 1 plus p1 r p minus 2 p plus p2 and so on. R p minus 3 p squared. And the last term or previous before the last term, let me see here. Yeah, the last term is going to be p to the power p minus 1. Now let's take this is mod actually mod p squared. We're going to see that all the terms, all right, well, let's see here. So this one is r p minus 1 plus p times r p minus 2 times p plus this one is, it had p squared. So this one, all these terms, of course, this has p squared factors. And even the first one, also this one, together with this all has p squared factors. So this is going to be congruent to actually, let's look. Let me have more space in here. I think. I'm lying a little bit in here, so let me write what this is equal to actually. All right, so we're going to continue from here. Okay, so this is equal r to the p minus 1. We expand there, so this is going to be p factorial over p minus 1 factorial times r to p minus 2 times p plus the other factors they all have p squared r to the power p minus 3 and so on up to p minus 1. All right, so this one it becomes r to the p minus 1 plus p minus 1, because this one is actually p times p minus 1 factorial, so it becomes p squared, yeah, r to the p minus 2 plus that's why. Actually, all this exponent needs to be p minus 1. I'm sorry, p minus 1. This one is the, we are raising this to the power p minus 1. Okay. All right, so we have, this is right. Okay. So this, sorry, correction. So the first term is, yes, r p minus 1 plus this one is p minus 1 factorial divided by p minus 2 factorial, then r to the p minus 2 times p then all of the other terms, they're going to have p squared. R p minus 3 up to p minus 1. All right, one more step, and then we're going to do a congruent mod p squared. So this is r to the p minus 1. And this is going to be p minus 1 and p minus 2 factorial cancel out. So we get this p r p minus 2 plus the remaining parts. Now, since one other thing in here, step. So all of these, they have p squared factor. Or also we still have one more in here, and this is p squared r to the p minus 2 minus p r p minus 2 plus all of these squares p squared factor. All right, we're going to now do congruent mod p squared. So this is congruent to r p minus 1. This becomes 0, and we end up with minus p r p minus 2, and all others gonna become 0 mod p squared, because they contain p squared as a common factor. All right. Now remember our objective. Okay, this coming back in here. We're going to show, remember this is our goal, to show that r to the power p minus 1 is not congruent to 1 mod p squared. All right, we're going to show this. So we have this one now. I claim that we have one other thing in here. Let me see in here. No, sorry. Not R prime. Sorry, I lost. So r prime to the power p minus 1, this one is not congruent to 1 mod p squared. We already actually we are working with the case where r to the power p minus 1 is congruent to 1 mod p squared. So this is true. So in other words, this, we can say it is congruent to 1 minus p r p minus 2 mod p squared. I claim that this is not congruent to 0 p r to the p minus 2 is not congruent to 0 mod p squared. All right? And to see this, we have, first of all, to prove this claim, we know that P does not divide R, because it's a primitive root, all right, for P, so it's relatively prime. It has to be relatively prime, and this implies that P does not divide any power actually of R, in particular P minus 2. And this is equivalent to saying that R to the P minus 2 is not congruent to 0 mod P, and we can multiply this congruence relation by P, so this one becomes P on P minus 2, still not congruent mod P squared. All right? Because if this is congruent to 0 mod P squared, then this becomes actually congruent to 0 mod P, and this is, of course, not true. So this takes care of this, which means that the R prime, that's what we have in here, R prime is congruent to 1 minus P R P minus 2 mod P squared, and of course means it is not congruent to 1. Because if it is congruent to 1, and this means that this is not congruent to 1 mod P squared. Because if it's congruent to 1, then means this P times R to the P minus 2 is congruent to 0 mod P squared, which we showed it's not. So in other words, yes, we do have this integer. All right. Let me see how much I have. There are several pages yet to cover. So probably I'm going to stop right here. The next thing I'm going to show is actually it's a corollary. So let me do the corollary because it's natural to do this. I'm going to then stop after that. All right. Let me do this corollary here. Which tells us that P squared has primitive roots. That P odd and prime, then P squared has primitive root. Moreover, if R is a primitive root, of P, then either R or R plus P is a primitive root of P squared. Actually, this is sort of what we have shown in the previous lemma. So if R doesn't work to satisfy that condition, then R plus P. All right, let's look at the proof here. We have since R is a primitive root, of P, then the order mod P of R is equal to phi of P, which is equal P minus 1. All right, then let's let M to be the order of R mod P squared. And this, by definition, means R to the M is congruent to 1 mod P squared. And also, since P is a divisor, of P squared, the R to the M is congruent to 1 mod P. All right? properties of congruences. Very simple to see. All right. Now let's see what we have. So we have this congruence actually does hold mod P, so it means that phi of P, which is P minus 1, divides M. So that implies P minus 1 divides M, because this is the smallest. All right? Now, we also have from the order M actually is the order of R mod P squared, that M divides phi of P squared. And this one is equal P times P minus 1. All right, well, let's look at what these two divisibility implies. So this implies that M, all right, is equal K times P minus 1 for some K, and this implies P times P minus 1 equal M L for some K and L. All right, let's put these together. So this means that P times P minus 1 is equal M. So we're going to substitute for M in here. All right, so this becomes K P minus 1 times L. Then we can cancel out P minus 1. So this becomes P equal KL. But P is a prime, so this implies that either K equal 1 and L equal P, or K equal P and L equal 1. Well, let's see what does this first possibility. If K is equal to 1, all right, and L is equal to P, this means this implies that M is equal P minus 1. And this would imply that M equal P times P minus 1. So these are the two possibilities. Now, if M equal P times P minus 1, this implies that the order mod P squared of R is equal phi of P squared. And this makes R a primitive root of P squared. On the other hand, if M equal P minus 1, then we are under the case if M equal P minus 1, this implies that R to the P minus 1 is congruent to 1 mod P squared. And by the lemma, we have R plus P is a primitive root. of p squared. All right, so in either case, we have a primitive root. All right. So let me look at just one maybe example. To illustrate these ideas. And then you're going to have another part for this section. All right, here is an example. So let's take P to be 7. It can be shown that R equal to 3 is a primitive root. Of 7. Remember, this means that it's equivalent to saying that the order mod 7 over 3 is equal to 3 of 7 equals 6. You can check this is the smallest exponent to which you raise 3 to end up with congruent to 1 mod 7. All right, now I want to consider the order over 3 mod 49, which is 7 squared. All right. We know that this one is going to be either equal to, so this one is going to be divides P of 49. And P of 49 is equal to 49 times 1 minus 1/7, which is equal 49 times 6 over 7, which is equal 42. All right? And which means that the order of the 3, there are 2 possibilities. This one is equal 1, 2, all the dividers of 49, 3, then 6, and 7. All right? And by checking, you're going to see that the order actually is going to be, this is or, we put in here, or 7. So by direct computation, you're going to see that the order of 49 over 3 is actually equal to 42. So it means that actually 3, this implies that 3 is a primitive root of 7 squared, which is 49. In fact, it is rarely the case that if R is a primitive root of a certain prime, R is not a primitive root of the square. It's rarely, okay, actually happens. Most of the primes, if you have an R is a primitive root of P, then the same R is a primitive root of P squared, all right? And the same thing with actually higher powers of P. Here's an example where this is not true. Of course, if R is not, then you take R plus P. All right? Here's an example where this is not the truth. Means R is a primitive root of a prime, but that primitive root is not a primitive root of the square. Then you will consider another one. I don't know if this is the smallest prime that actually satisfies this, but it's a larger prime, relatively speaking. So P is equal to 487. R equal 10, which you can do the calculation, is a primitive root. Of 487. 10 is not a primitive root of 487 squared. You can see the calculation is going to be tremendous if you want to do this by hand. Okay? However, 10 plus 487 is a primitive root of the square of 487 square. Of course, I'm not doing the calculations in here, but this is something, of course, you probably need to do it in a computer. I don't think you're going to do even with a hand calculator to do all the calculation that is, well, you're going to find what is field this, and then see that this is the smallest exponent, which you raise the 10 plus, which is 497, to give you congruent to 1 mod the square. All right? But that's what it is. All right. So in the next part of this lecture, we're going to look at another lemma that get us closer to show that different powers of prime bigger than 2, you know, p to the third and so on, they're going to have primitive roots, and then we're going to put this together to show that what theorem 8.10 states those numbers which they have actually primitive roots. All right, there's a project.